this up. So if you want to ask me any questions, yes, I have this number icon. Either put it in the chat or just turn your camera on and I'll wave your hands. So you can interrupt me any moment. I'll try to handle this. If there are no questions during the presentation or during the demo, we can deal with it at the end. All right. So I will start sharing the screen. So what we have here, I am logged on to the Leica SP8 system. And I already started the software. So you should be able to see once I find my Zoom application here, I will share my screen. So you can see my program. I'll try to make these letters a little bigger so that it's easier to see it on your screen. And what I have not done yet is I have not put the slide on. So that'll be just another minute. But we'll start with a regular Superresolution demo slide, which is a nuclear power complexes labeled with an antibody with a secondary label star 635, one of those special dyes for Superresolution, but you could also use Alexa 647 and similar. I'll be right back. So what I'm doing, I'm switching to a 100x objective because that's the only objective that is designed to be used with steps resolution. On some other Leica systems, you may also find there is I believe an 80 or a 63x objective, and then this is the one that we have. So we just have to make do. This. Okay, so let's just get an image on the screen, and what I'll have to do first is select the right die. So let's select the star 635P, and we'll be using one of the hybrid detectors on the system. The advantage of that is that it has higher sensitivity, and also it allows us to do fluorescence lifetime, which will be important in the tau STED system. So we have the dye selected. We'll be using hybrid detector number 2 over here. And let's just give it some nice pseudo color. For instance, red is a good one. So it's a cool detector, and we'll be looking at fluorescence starting somewhere at, let's say, 640 and up on that. And we'll be exciting with a 633 nanometer wavelength from our white laser. And our setting to somewhere around 3% laser power. So let's see what image we can get on the screen at this moment. We're zoomed out quite a bit. And so here, if but I hope you can see that we have signal. So these are, the slide has cultured cells, and these shapes that you see here are the nuclei of these individual cells with lots of little dots that are currently hard to resolve. So we're going to zoom in on one of these nuclei. Let's see if we can get this one a little bit closer to the center. And see if we can get that image a little better looking. I'm turning up the gain on the detector, and just to make sure that we're not overexposed or saturated, I'm switching to this pseudo color scheme. This lookup table should show me blue where we have some saturated spots, and we actually do have some of those, so I'll turn it down a little bit. So we're reasonably zoomed in. I'll leave it at grayscale, that's easier to see. With our fast preview, we're just doing 512 pixels square, but we're zoomed in, so currently our pixel size is about 58 nanometers. If the software can suggest the optimum size, and currently it actually is telling me that we're zoomed in too much, that I don't even need 512 pixels to resolve the features that the objective is capable of. Yeah. So that's for regular imaging. So I'm going to go a little slower, but before I do that, let's set up a stack of images, and we'll capture that, and then we'll switch to STED super resolution and see how we can improve the image that way. So these stacks, so I'll go live, and I will set the start of beginning of the stack, and then we'll zoom focus through the nucleus all the way to the far side, and so at the end, the software automatically suggests the step size, which is about 0.3 micros. And so that should work reasonably well. So what we will want to do for the actual acquisition, to slow it down a little bit so that we have better signal and less background noise. So let's see how it looks with 400. Yeah, that's a little better image. If I stop the live scan and hover over this, we're getting reasonably good intensities in the 2000 out of the 4000 that I said. So let's just go ahead and capture a Z-stack, and we'll look at it a little closer just to see what is resolved and what is not. So that's our Z-stack. I'll go back up, and if I zoom in, you'll see that there is a number of these nuclear polar complexes that show up sort of well separated, but there are also some where you can guess there is more than one, but it's hard to tell really how many. I'll try to take a slightly better picture, and we'll try to average maybe 4 lines so that we get the better signal to noise ratio and just collect more photons. So let's try that. I'll go back to live image and try to focus on the surface. Yeah, we'll just take a single image like that. So I'll just capture one. Yeah, it's a slightly clearer image, but it's still, we're hitting the resolution limit of standard optics. So on this system, it now is fairly easy to switch to a state super resolution. But before that, I have a couple people that maybe either were not watching my super resolution presentation, or I figure we'll just do a little brief refresher on what is that and how it works so that it's a little clearer what we're doing. So let me just move this. This is from the Leica online help. And so this is a page that talks about STED. So let's make it a little bigger like that. So what you get here is the principle of the STED system is that we're illuminating a spot on the sample, we're scanning in that spot. But because the spot itself is diffraction limited, we are hitting the resolution barrier. We cannot really get better than about 200 nanometers in XY. But on this system, what we're doing is we're superimposing on that excited spot, that all MX photons, we superimpose this donut-shaped longer wavelength laser. It's 775 nanometer laser that has, that has a zero intensity in the center. And so what that laser does, it forces all of these excited molecules down in the periphery of that green emitting spot down to the ground state without emitting the photon that we would normally expect. So effectively, we are reducing the excited spot size quite a bit. So now when we scan with that spot, we can achieve much better resolution. And overall, the higher power of the donut on the STED donut you apply, the more you can squeeze the excited spot. So the more you improve your resolution. So that's how it works. And there is a little trick to it that I'll cover later, because we have, that's the regular STED that I'll show, and then we have this new addition, which is called TAMU, which also uses the fluorescence lifetime information. And I'll just come to that later. So first look at the regular STED. So you're seeing that's the regular confocal image. So what I'll do now here, I'll click this button to activate the STED system, and I'll turn the STED laser on. And right now, we already have zero intensity of the STED lasers, so we should still be getting about the same laser, the same resolution as we had before. So diffraction limited. what I should do is now I will, if I increase the laser power to something like 30% of that stud laser, the system automatically calculates how many pixels I need really to cover that resolution. So if I hover here, it will tell me that instead of 380 pixels, I need like 1200. So let's click here. So it will make for a really big image, and it'll be kind of slow, but I don't know if you can read the numbers. But 1 pixel now corresponds to about 23 nanometers. So what I'll do, I'm just gonna zoom in some more so that you don't see it on the screen. But I'll zoom in some more so that we get to about 20 nanometer pixel size, and let's see how that's gonna look. So we go live. So these are our spots, still regular imaging, and now when I start increasing the stud laser power, you should see an improvement. So let's go to something like 18%. I'll have to tweak the settings a little bit and increase the laser power. Oh, here we go. So let's grab an image and see if it's any better than the previous one. It's sort of better, except we probably shouldn't be. So if you look at it here, and then we look at this image here, yeah, nothing really to write home about. And that's probably because we've got potentially some alignment issues. So typically at the beginning of the experiment, I go to configuration, stud, and then we'll say align beams. Because those beams, the stud beam and the excitation beams here have to be very precisely aligned. And luckily on this system, you don't have to spend an afternoon tweaking the lasers in the dark. There is a test target and automated routine. So we'll see if it actually works. So it's doing its alignment. And it says alignment was successful. So we can go back to acquisition. And to make life a little easier, we actually have a wizard here, which is called the Smart Stud. So I'll just go with that. That's that. And so in the Smart Stud panel, here I can choose how much stud power I'm using, and you can see that correspondingly, we're narrowing the point spread function. So let's go down to 0 and do a confocal live image. Okay, and that's kind of, pretty noisy, but you see those spots in that live preview. So let's do something a little bit different. So let's do the confocal preview again. So there we go. And then I can do the stud preview. And you can see that it's quite a dramatic difference. So let's capture an image. So this is your stud super resolution. And if we go back to the live, and I can set the step to 0, and if I capture another image here, that is your confocal. So now we can show those two images side by side. Let's add this one and make it a little bigger. So here on the left is your regular confocal, and we'll zoom in on a group of these nuclear pore complexes. And then here, let's make it a little brighter. Now we can resolve easily, it's quite a difference. So these, lots of these spots, like in this case, there are actually what seems two nuclear pore complexes in this, very close together in this spot. And there was really no way to see that on a regular confocal image. So it's fairly easy. Now the downside of this system, if we go back to acquisition, let me just see, the more you turn the power up, let's just go really aggressively. Yeah, let's do something like 70% stead settings. And I'm going to just cancel this one. Let's do another confocal live preview. Let's do the step preview. And we turn the power up quite a bit, and that also means that we're making the whole image much dimmer. Let's see if we can handle that. It's kind of hard to focus when it's so dim. And that will, show you some limitation of what the step can do. But let's try that. I think I am a little bit in the wrong focal plane. But if I turn it up, the contrast a little bit, yeah, then you should be able to see maybe smaller dots. So the resolution has improved, but at this step power, we're depleting so much fluorescence that it's hard to see it. But if we increase our number of line averaging and maybe use a little stronger excitation, that should work. But if I go back to the confocal live, and what typically happens though, let's see what happens now when I start zooming out. You see that we were able to bleach a really nice rectangle with our high power stud laser. Yeah. So that's the big issue with stud, that you need really strong emitting dyes that are very stable, and even then it's very easy to photo bleach them at high stud powers. Any questions so far from the audience? I'm gonna stop the share so that you can chat out, hopefully. I'll put my headphones on. Anybody? I have, so the question was whether the recording will be posted. And I have recorded a separate video that shows the stat and post-stat effects, and I'll send that to Ashley. I need to finish a little bit of annotation on that, so we can do that. I didn't tell you, but you're welcome to just record this on your end if you want to. But I kind of forgot to click the record button.
I went ahead and recorded. So if there's anything that happened, I went ahead and recorded. I'm recording it. So if anything comes up in the questions, that would be helpful. We can edit that down and add it to the other video or whatever.
Okay, I could almost hear you.
Oh no.
All right, so yes, there will be recording one way or another. And of course, you're welcome to just email me, and we can talk on the Zoom separately, you know, on matters related to your project too, and talk about dyes and such. So this was the step superresolution, so stimulated emission depletion, and in principle, this technique has unlimited or almost unlimited resolution. We are limited by the stability of the dye and how much power we can deliver into that depletion donut. So in a published paper a couple of years back, they were able to achieve a resolution, XY resolution about 6 nanometers. But that was on some nanodiamond or diamond fluorescent particles, with some nitrogen vacancy or faults in diamonds. So those things never photo bleach, and so they were able to image it with very high powers for a very long time to get to this resolution. Practically speaking, with a regular kind of well-prepared sample and the correct dyes on this machine, we should be able to get, at least they claim, down to about 40 nanometers in the XY. Now, on our machine, we only improve resolution in XY. If we needed to do improvement in a Z direction as well, we would need another about $100,000 to add a second laser and to be able to do the depletion in 3 dimensions. I'm gonna do a screen share again because I need to show you the. Okay, where are we? Here. I'm gonna go on this screen, and then I'll drag this presentation on again. So if we wanted to do, so typically we do a two-dimensional donut. That's what you just saw. That's a depletion laser to squeeze the spots. So in the Z direction, that spot still has about 500 nanometer, from the center to the first minimum. So about half a micron Z resolution, and that we show here. So we squeeze the original point spread function from that shape down to this really long spindly shape, but we're still limited unless we apply steady laser also in the shape below and above that. And so that's another laser and some added complexity to the system, but it's possible. Now, that is all great, but for many samples, it's not practical because we need too much laser power, and we would either bleach the dye or we would kill the live sound. So now that brings us to a practical matter. What can we do on our particle microscope? So our stud laser is 775 nanometers. And from the fluorescence point of view, the dye that we're trying to detect, let's say Alexa 647 dye or any other dyes, their emission has to have a partial overlap with this red laser. Otherwise, the stud phenomenon will not occur. There won't be absorption really of that photon. So it means that we can only use, essentially we're stuck with synthetic dyes, or those nanodiamonds, things that emit infrared. And as a second color, we can also at the same time do dyes that are excited around 600 or 500 nanometers. So you could have, let's say, Alexa 647 and Alexa 594, and we could get 2-color super resolution. We cannot, so the only fluorescent protein that would be compatible with our system is the M-Neptune, and possibly maybe some of those longer proteins, like I believe there's like an M-Plum, and there are some longer ones, but those are not terribly bright. So the M-Neptune is really one of the few options. For things like green fluorescent proteins and other dyes in the middle of the spectrum, we would need a different stud laser. The problem with that would be that typically you also get higher fluorescence factor. So that's your classical stud. So what we'll do next is we'll go and use something called tau stud. Let's see. And this is an addition that we only have for about a week. And so on our machine, we can measure fluorescence lifetime. Yep. Essentially, we excite the molecule. Now, where is my element? We excite the molecule. Yep. We shoot, let's say, a blue photon and get some green emission. Or in our case, we shoot kind of reddish photon and get even further red emission. The molecule stays excited for several nanoseconds and then randomly at random time emits a photon and goes down to the lower energy state. So how long that molecule stays excited before emitting a photon is corresponds to the fluorescence lifetime. And what's interesting in this case is here. Let's go here. Is that we can use that lifetime in the stud super resolution. Because here, because when we apply that donut shape depletion to this excited spot, once we apply that stud laser, it forces those excited molecules down really fast. So essentially, on the where the donut is, the fluorescence lifetime is much shorter than in the center of the donut, where it remains close to the origin. So if we had, let's say, Alexa 647 or Star 635, the lifetime is maybe 2.5 nanoseconds. It will stay there in the middle, but if the donut, where the donut is, it would go down the more we apply the stud power. Let me demonstrate that, because I think that's going to be quite useful. I will exit our smart stud wizard and go back to regular imaging. Just make sure I can see what I'm doing. So the previous image where we bleached that nice rectangle, we were using a pretty high step laser power, 56%. That's quite bright. And we also had, the software also turned up excitation power to really high value. So we're gonna go back to some more reasonable numbers, around 3% excitation, and I'm going to turn the step laser down, currently down to 0. Let's see how it's gonna look. All right, I will, let's just pick another nucleus that just to make sure that we don't look at the same bleached area. So we're going to zoom in. Essentially, we're right now at a confocal mode, so nothing special. And I'll bring it here in the middle. And again, I'm zooming in so that we have approximately about 20 nanometer pixel size. So now I'll have to kind of tweak that a little bit. So we'll do a little smaller area. So zoom in, we're at around 20 nanometer pixel size in a regular confocal image. And I'll make it a little brighter so that you can see it. So far so good. And then let me just show you what's happening with the, because we can very easily measure fluorescence lifetime. So I'll turn on this flame module, and it will show on a second screen, which you currently cannot see, but I'll drag it over in just a moment. Yeah, so I'll start the live view, and you'll see on this image. All right, so okay, let's just show this view. So on this image, the image that you see here is the fluorescence lifetime. And with our phasor analysis, actually, let me just stop the preview and go to here. This spot corresponds to the fluorescence lifetime. On this plot, the further on this semicircle to the left, the longer the lifetime. Yeah, and I can go here and select these lifetime, and it tells me it's about 1.6 nanoseconds on average. So I'm going to leave this on running, but what I'll do, I'll start applying higher laser powers. So what, and I'll just let you see the, the lifetime as it's changing. So I'm starting the live view again. And then we're going from 0 step power to something like 14. And you can see how the lifetime moved. So let's just go to the surface here. So if I lower the lifetime, if I lower the step power, the lifetime gets a little longer because not as many molecules are forced down to the ground state fast in the donut area. So that's just for you to see the lifetime. Let's just make sure that it's in focus. So what we then can do, we can use the software to to acquire the fluorescence lifetime image and figure out the super resolution information from it based on the lifetime. So I set the step power to 5%, and then we go to something called the Townsend option in this software. And we'll just stick with a reasonable settings here. And what will go to Townsend. And all I did is we're just going to take maybe 10 frames and average them. So let's go ahead and do that. So it's taking images and averaging them. And we're only at 5% stead power, which in the regular stead mode, we could barely see any difference in the super resolution. But here, there is a clear difference between this image, and let me just move the other picture on the screen. I'm gonna make it a little smaller so that we can see both. Okay, maybe here. All right, so if I zoom in at this group, and then I zoom in here at the same group, we'll turn up the contrast. It's we definitely are getting an improvement in resolution compared to the regular confocal. So confocal here on the left, and we also are getting better contrast, which will help us resolve some of those features. So I would say overall, so this spot and those two spots are thoroughly resolved here. And on this image, let's move it. Make sure that we're looking at the same thing. Yeah, so those 1, 2, 3 spots here, 1, 2, 3 spots, those two spots much better separated. And then we have this jumbo here. Those two spots are separated as 2, but we could not then separate that on the regular component. And that's only with 5% power. So we could go. You have also manual options in because I could do the manual, and here is essentially what in the phasor plot what it shows you, that the system automatically drew a line from those the background, which has the shortest lifetime, through that phasor spot, the longest lifetimes, which represent the center of the donut or part. That's our excited spot. So one could obviously move it a little bit. It can, change the appearance slightly. And there are some of these settings that you can play with, but overall, it seems like a very straightforward and easy way to get reasonably increased resolution without much stead laser power. And you just click a couple buttons, and if everything works the way you want it, you'll get your super resolution image. So what I could do here, I could go and we're at 5% stead power. Maybe we'll go to something like 10. Okay, let's go to 10. And you can watch here on this lifetime window what's going to happen with phasor plot. It's going to move down to shorter lifetimes. I would imagine. Yeah, so I think that was that. You can also see that the resolution improved further with our increased laser power, but we're still in a good conservative range where we're not going to bleach the sample too much. So in practical terms, when doing regular stat, we have to be somewhere 10, 20, 40% step power. And with the tau stat, which uses the lifetime info, you can get a noticeable increase in resolution somewhere about 2 or 3% step power. So anyway, that's the short of stat super resolution. Now I see questions. Okay, let's see what's happening here. Okay, yes. So, are there any special sample prep requirements for STAT? Well, your sample, since now we have a higher resolution, you have to make sure that your sample is not does not have artifacts due to sample prep. So some strange shrinkage and destruction of organelles because maybe your sample degraded during preparation, or because it was dehydrated too fast and it shrunk and all of that. So yes, Leica has some guidelines for sample preparation for STAD. And part of it is also using the correct mounting medium. Here we're using the 100x oil immersion objective. And so ideally, to get the best image and the smallest aberrations or degradation in image quality, we would also need the mounting medium that has the same refractive index as the immersion oil. So there are some commercial options. For instance, I know that Thermo Fisher offers something called prolonged glass, and that's a non-hardening medium that has the same refractive index as glass of oil. And there are other companies. I know Citiflor has one of those. People also use some other homemade media that would have that same high refractive index. So that's and I'm gonna send Ashley the link to that to the guidelines for sample preparation. So this was one super resolution option that we have here. It's it's all hardware based, so you don't necessarily have to do much of post acquisition processing and tweaking, and it seems okay. Yeah, there's another question. Will STAD work for 3D samples that have been cleared with thiodiethanol? Well, if you have the right dye in there, that should work. I don't know what percentage of thiodiethanol you have in it, but ideally it would be 97% PDE, and that will have the same refractive index as glass or oil. Depending how thick the sample is, the deeper you get, the worse it will be if you don't have the refractive index matched precisely. But yes, yeah, definitely, as it should work. Okay. Well, if you, there is, okay, yeah, you're welcome. If you know somebody who wants to take the light microscopy class, Biology 608, next semester, tell them to sign up. so that I have at least some virtual audience when I'm teaching it in the spring. All right, and I guess it'll be easier to do demos now that everybody's used to Zoom. So all right, that's it. I was going to show you some other super resolution techniques previously, but and that I mentioned in my talk that Ashlyn posted before Thanksgiving. We have the DSOS processing. That's free software that you can use. And I played with it a little bit, but I think it'll just need a little bit more practice for it to be convinced that that's really useful. So anyway, I'll let you know if there are any news on that front or other fronts. And we did not do. I wanted to show you something regarding deconvolution, but I forgot to ask the person whose sample it is for permission. So I don't think you'll get to see it. Otherwise, I didn't want to do it without them being okay with it. So that's maybe for some other time. Okay. Well, if there are no other questions, well, if you think of a question, just shoot me an email.
Thank you, Stan.
You're welcome. I could actually hear you. It's coming from somewhere in the system, but I don't know where.
Oh dear, after all this time.
Okay.
Thank you.
Okay.